So endocrine organs, endocrine glands, can be described as being central or peripheral. That's one category or categorization. And central endocrine disorders are called central because they are literally part of the central nervous system. Okay? So central endocrine glands are part of the central nervous system. Okay? Peripheral glands are in the periphery. They're not part of the central nervous system. And often they are not part of the nervous system at all. Okay? So several structures, several central endocrine glands are of particular interest for understanding normal physiology and development of many diseases. And two of those structures include the hypothalamus and the pituitary gland. So the hypothalamus, that sits at the base of the brain. Okay? It's a neuronal structure. It's composed of neuronal cells. But many of these neuronal cells are called neurosecretory cells because they synthesize and release hormone. And the hypothalamus is connected to another gland called the pituitary gland. Right? There's this tiny little connecting stalk that attaches it to the pituitary gland. And the pituitary gland sits in this bony encasement, right, to protect it. And there are two portions of the pituitary gland, the anterior lobe and the posterior lobe. This posterior lobe is greatly exaggerated in this picture. Right? The majority of the mass of the pituitary is in the anterior lobe. And the connection between the hypothalamus and the pituitary is very different between anterior and posterior. Okay? Now, between the hypothalamus and the posterior pituitary, what's the nature of that connection? Posterior pituitary is an extension of the hypothalamus. Okay? It's a neurological extension of the hypothalamus. There are actually no glandular secretory cells within the posterior pituitary. The neurosecretory cells that originate in the hypothalamus, their axons run through the connecting stalk, and their axon terminals are located within the posterior pituitary. And there's two hormones that the hypothalamus releases from the posterior pituitary. And that's vasopressin, or antidiuretic hormone, same hormone, two names, okay, and oxytocin. Now, they are released from the posterior pituitary, but they are produced and controlled. Their release is controlled by the hypothalamus. Okay? Vasopressin and ADH we will talk about a lot in the renal system. It is important in water balance, right? Controlling the retention or excretion of water. And also, it's a vasoconstrictor. And then oxytocin plays an important role, as I mentioned, during labor. It also plays an important role in breastfeeding. And then oxytocin is thought to have a variety of very interesting roles in the brain, including mediating things like social bonding, okay, parental bonding. Of course, my husband sent me this article. He is a bigger science nerd than I am, so that tells you something. He sent me this article about, they studied men and oxytocin levels with age, especially oxytocin levels in the brain with age, and it tends to go up. Your oxytocin levels will also increase when you like transition from like, if you were married, if you transition from like pre-kids to after kids, like your oxytocin levels go up. And they found that men with the highest oxytocin levels tended to be those that were the most fidelitous, so least amount of infidelity. So the, what is that? What's that? Faithful, thank you, yes. Fidelitous. Yes, faithful, thank you. Yes, so, and then men with on the lower end of the oxytocin scale tended to wander a bit. So it was very, very interesting. And like the tagline for him was like, my oxytocin level is through the roof, you know, so. We have a good marriage. It's nerd plus nerd. All right. So that is the relationship between hypothalamus and posterior pituitary. Relationship between hypothalamus and anterior pituitary is literally the communication between two endocrine glands. Okay? So the hypothalamus releases hormone that actually act on cells in the anterior pituitary to trigger or regulate the release of other hormones. So the GnRH-LH that I talked about earlier, GnRH is released from the hypothalamus and acts on LH-releasing cells in the anterior pituitary to stimulate the release of LH. And there are several anterior pituitary hormones that are controlled in this axis, right? This hypothalamic anterior axis, anterior pituitary axis. It includes LH, FSH. You don't have to worry about this list, but LH, FSH, prolactin, right? ACTH, TSH. Okay, so a whole host of hormones released from the anterior pituitary is controlled by hypothalamic hormones. Now, this connection between the hypothalamus and the anterior pituitary is two parts of actually three, or two glands of actually three different endocrine glands that control hormone release. So in this particular axis, we've got endocrine gland number 1, in this case is the hypothalamus, releasing some hormone 1, acting on gland 2, which is anterior pituitary, releasing some second hormone. And then all of them have a third endocrine gland in the body that triggers the release of a third hormone. And normally, it's this hormone, this third hormone, that actually acts on target tissue to bring about the physiological responses. So in the thyroid hormone example, which we'll actually see a little bit more closely in a moment, the hypothalamic hormone is called TRH, or thyroid releasing hormone. That acts on the anterior pituitary to release TSH, thyroid stimulating hormone, which then acts on the thyroid gland to release T3 and T4. Okay. TRH, or thyroid releasing hormone. The second hormone was TSH, thyroid stimulating hormone, and the third is T3 and T4. Okay. Now, all of those hormones I mentioned earlier, released from the anterior pituitary, participate in their own axis like this. Okay. Now, this is an example. It is a negative feedback loop, okay, because hormone number 3 and hormone number 2, for that matter, provides negative feedback to the glands above it to ultimately control the levels of hormone 3. Okay. And this kind of negative feedback is called the hierarchical level of control, right? So there's a hierarchy of glands and of hormones, and then there's feedback within the hierarchy. Okay. And the advantage of this is by having 2 points of control instead of just one, you actually create better overall control of hormone 3 than you would otherwise. Okay. It's just better control because you have 2 points of control rather than just one. All right. So if we look at this example, we look at the thyroid gland. Okay. So the thyroid gland is this gland that has 2 lobes and a little connection, sits on the trachea, okay, at the bottom, sort of near the clavicles. And the thyroid gland is that 3rd endocrine gland, right? So you've got the hypothalamus releasing TRH, acting on the anterior pituitary to release TSH, and that acts on the thyroid gland to release T3 and T4. And T3 and T4 provides negative feedback at the level of both the anterior pituitary and the hypothalamus. Okay. Now, T3 and T4 is released in both a constant way and also in a diurnal pattern. And it controls baseline metabolic rate, baseline heat production. It has some enhancement of growth, especially of the central nervous system, right? Enhances sympathetic activity, right? It has a wide variety of effects, but the most notable effects is in elevation of energy consumption and metabolic rate. Okay. Now, we will talk actually quite a bit about thyroid disorders in the next part 2 of this class. But just to illustrate sort of the dynamics of the negative feedback with these hormones, if you have a problem with the anterior pituitary, if there is, for example, the TSH producing cells are non-responsive, okay? And they're non-responsive to TRH. So that means the hypothalamus would release TRH, the anterior pituitary would be non-responsive, and would not release TSH. And what would that do to T3 and T4 levels? It would decrease. So when you looked at these 3 hormones, what you would see is low T3 and T4, low TSH, and then what would TRH look like? It would be, what would it be, normal, low, or high? High, because of a lack of negative feedback. Okay? So looking at the levels of these 3 hormones actually tells you actually where is the problem, if any of the values are abnormal. Okay? So if I told you that TRH was high, TSH is high, T3 and T4 is low, where is the problem? At what level? The thyroid gland, right? Because TRH is high, TSH is high, T3 and T4 is low. This is the first inappropriate response. High TSH should produce high T3 and T4, but it's not. And then the lack of negative feedback creates an elevation of TRH and TSH. Okay. So these hierarchical control loops are very important to understand, and it applies to a variety of hormones released in this pattern and creates predictable problems. Yes?
But the production of TSH doesn't cause a tonal feedback loop to bring the TRH back to normal levels in that situation, does it?
No, because so the question is that the TSH feedback, does it sort of correct it to bring TRH back down? The most important signal is the third hormone signal. So the direction that this hormone goes is going to have the greatest influence on what the preceding hormones do. Okay. So another peripheral gland that's of great importance to us, even before we do endocrinology next semester, is the adrenal gland. Okay? And now the adrenal gland looks like this little blob of a structure that sits on top of each kidney. Okay? And if you look at the interior of this gland, which is what this is sort of sliced open, what you see is the interior, right, this yellow part, is called the adrenal medulla. And the layers outside of that are called the cortex. And these are essentially two very different endocrine glands. Okay? So the adrenal medulla is actually part of the sympathetic nervous system. And it releases epinephrine, a little bit of norepinephrine, right? If you're British leaning, adrenaline, noradrenaline, okay? So it's part of the sympathetic nervous system and controlled by the sympathetic nervous system. The adrenal cortex is an endocrine gland that produces steroid hormone. The adrenal cortex is an endocrine gland that produces steroid hormones. Okay? And the production of those steroid hormones are controlled by other hormones, right, interacting with the cortex. So this is the variety of steroid hormones produced by the adrenal cortex. There's 3 different layers of the adrenal cortex. Different layers produce different things. Now, all steroid hormones are synthesized from cholesterol, that guy up there. Okay? Now, starting from cholesterol, you can produce the various end hormones based on what enzymes these intermediates come in contact with. Okay? So if you look at the hormones that the adrenal cortex produces, there's 3 categories of hormones. Glucocorticoids. Okay? Glucocorticoids. Glucocorticoids include this blue box: corticosterone, cortisol, cortisone. Right? These are stress hormones, and the reason why they're called glucocorticoids, because one of their many actions is they elevate blood glucose. Okay? So blue box: corticosterone, cortisol, cortisone. Second category, mineralocorticoids. Mineralocorticoid, which there's one, and it's this pink box, okay, called aldosterone. Okay. Mineralocorticoid, it's called mineralocorticoid because of its effect on sodium and potassium. It tends to cause retention of sodium and potassium loss. So mineralocorticoid, glucocorticoids. The last category are the sex hormones. Okay? Are the sex hormones. And it includes progesterone, different forms of estrogen, which is not in this slide, and the masculinizing hormones as well: testosterone, DHEA. There's some different forms of masculinizing hormones. So feminizing hormones and masculinizing hormones, the sex hormones. Okay. These sex hormones, both categories, produced in men and women by the adrenal cortex. Okay? Yeah.
Did you think it differentiates from the cholesterol with the interaction with the adrenal?
Yeah. So starting from cholesterol, starting from cholesterol, the first thing to be produced is something called pregnenolone, and that's a common precursor to all of them. And if you notice that each of these molecules are moving through a bar, either across or below it, that bar is an enzyme. Right? So if pregnenolone moves across, it can produce progesterone, and if it continues to move across, it can produce a glucocorticoid. Or it can move ultimately across and produce aldosterone. Or it can move down and produce one of the masculinizing hormones, one of the androgens. Okay. So it's kind of the part of these steroid hormones is that really everything is derived from everything else. Okay. And while all the intermediates are lipid soluble and move freely from layer to layer, the enzymes are proteins, and they are only located in certain cells, right? But the consequence of how closely related these structures are, one of the consequences are, for example, the glucocorticoids are not actually all that different in structure from the mineral corticoid. So what you find is that these forms of cortisol have mild mineralocorticoid action. So these forms of cholesterol produce a certain amount of sodium retention and potassium loss. Right? So because they're so structurally different, so structurally similar, you can end up with a little bit of crossover of effects. Okay. Aldosterone, we talked about in the renal system. The masculinizing and feminizing hormones we talk about a little bit in some of the pathological endocrine disorders. And if you have maternal fetal newborn physiology with me this summer, we talk a lot about that. So let's look a little bit more about cortisol. Okay? Now, I tend to only refer to it as cortisol, but all three of those glucocorticoids are really of equal potency. So corticosterone, cortisol, and cortisone, thank you. I answered that question. All right. They are all sort of, the production of all three of those are controlled in the same way. I just sort of shorthand it and refer to them all as cortisol. Okay. Now, cortisol, the production of cortisol is controlled again by one of these hypothalamic pituitary connections. So the hypothalamus releases a hormone called CRH, or corticotropin releasing hormone, which acts on the anterior pituitary to release adrenocorticotropic hormone, or ACTH, which acts on the adrenal cortex to increase production of cortisol. Okay? And then cortisol provides negative feedback at the level of the hypothalamus and the anterior pituitary again. Now, I told you earlier, cortisol is produced in a diurnal pattern, right? Its levels reach their peak just upon waking or just before waking, and reach their lowest point right before going to bed or right before sleeping. However, you get a release of cortisol under stress-related conditions. It's part of the human stress response. So in addition to maintaining some baseline functions, an increase in cortisol also produces some acute effects. So what are the effects of cortisol? Cortisol acts on a lot of target organs to do a variety of things. Now, up here, if you notice, there's a picture of the liver. And cortisol is a glucocorticoid, so it's called that because of its ability to elevate blood glucose. And it actually does that in a variety of ways, including stimulating the liver to break down stores of glycogen and also to increase its production of new glucose called gluconeogenesis from things like circulating amino acids. Okay? So it increases the liver production of glucose. Cortisol also acts on skeletal muscle. It tends to actually break down skeletal muscle in order to release amino acids. Where do you think those amino acids are going to go to? To the liver to help produce more glucose. Okay? Now, keep this in mind. Cortisol-related reactions are designed to be short-lived stress responses. Okay? You're not supposed to have persistent release of cortisol, although some people do, right? And that's a pathological thing. But a short-lived release of cortisol only produces a small amount of muscle breakdown and a boost of glucose. Pathologically high cortisol levels for a prolonged period causes muscle wasting and hyperglycemia. Okay? So these are all, think about this both in the short-lived, intended scale and also at the larger, more pathological scale. Cortisol also acts on bone, and it causes the breakdown of bone and the releasing of calcium into the bloodstream. Okay? Now, still on the topic of glucose, sorry, I talked about the bone thing too early. Still on the topic of glucose, glucose also it also acts on cells that are sensitive to insulin, and it antagonizes those receptors a little bit. Okay, so cortisol antagonizes the insulin receptors a little bit, and that reduces that insulin-mediated uptake of glucose. And it's keeping glucose in the blood. And the reason why it's keeping glucose in the blood is because there's one part of our body that can really only use glucose for energy, while other tissue can use glucose or fat. And what do you think that structure is that can only use glucose for energy? That's right, the brain. Okay, so it's preserving glucose for the brain. You need to think on your toes. You need to decide, is it worth fighting or should I just turn around and run? Okay? This is a stress response. Now, cortisol also, I'm skipping a few things, so just trust me why I'm skipping them. It also has some mild mineralocorticoid action, so it does produce a certain degree of sodium retention and potassium loss. Okay? And that's also good, right? We're getting more calcium in the body, we're getting more sodium in the body, because calcium and sodium are necessary for muscle contraction. Right? If we're going to fight or flee, we got to use a lot of muscle contraction. It also enhances the excitability of the brain. It increases mental agility. Okay? Allows you to be able to think fast, think clearly, of course, too much cortisol, thinking goes out the window, right? And if you've ever stayed up all night and stressed over a test and tried to then go in and take that test, you know what that's about, okay? And then cortisol also is a potent anti-inflammatory hormone. It has potent anti-inflammatory effects and somewhat immune suppressive effects. And when I did the immune system, I actually talked about how steroids, cortisol, blocks the production of arachidonic acid, which is necessary to produce, don't worry about this, but necessary to produce prostaglandins and leukotrienes, which are part of inflammation, right? So that's how the cortisol blocks inflammation. And like I said, it also has some immunosuppressive effects. And the idea, again, is that you don't want, this is a time where you're shuttling all of your energy to respond to this stressor. Okay? You don't want to dedicate any energy at this time to your immune function. You can take a break from that for a little while. Okay? So those are the effects that cortisol have on the body. So the pancreas is another peripheral endocrine structure. It's a peripheral endocrine structure that we're only going to talk briefly right now about the endocrine portion of the pancreas. We will talk much more about these hormones in patho in the context of diabetes, and we'll talk more about the pancreas and the digestive system. So the pancreas is an organ that is both an endocrine organ and an exocrine gland. Okay? So there is a portion of the pancreas that is endocrine, produces hormones into the bloodstream, and then there's a portion of the pancreas that is composed of exocrine tissue. And the exocrine portion is what we talk about in digestion. The pancreas produces pancreatic juices, which include sodium bicarbonate solution and lots of enzymes that break down food. Okay? And so we'll talk more about that. But the endocrine portion of the pancreas is composed of these functional subunits that we call the islets of Langerhans. Okay? So islet is, in some language, I'm not sure which, means island, right? And Langerhans is the guy who got to put his name on the pancreas. So it's these islands of cells, it's these groups of cells that are just surrounded by capillaries, and there are several cell types in these islets. Now, the two most important cell types for our purpose are the alpha cells and the beta cells. The alpha cells produce a hormone called glucagon, and the beta cells produce a hormone called insulin. Okay? These are classic antagonistic hormones. Okay? So when you consume food and your digestive system absorbs that food, it absorbs the glucose in that food. Your blood glucose rises, and that triggers the release of insulin. Okay? Insulin's job is to promote the uptake of glucose, right, by very particular cell types in your body. And there's three main cell types: skeletal muscle, fat, and the liver. Okay? So you consume a meal, your blood glucose starts to rise, insulin is released. Okay? Insulin's released. And then insulin promotes the uptake of glucose by skeletal muscle, fat, and the liver. Okay? And for all three of those cell types, the glucose that it takes up, it's going to store. In the muscle and the liver, it stores it as glycogen. In the fat cells, it stores it as fat. Okay? Now, after you've eaten your meal, you then go about your day and you do something that most Americans don't do, which is go more than like an hour or two without eating something, right? Me too. So you go about an hour or two, 3, and then what starts to happen is that your body shifts into what's called the fasting state. Okay? It shifts into the fasting state where it's trying very hard to maintain an adequate level of glucose in your bloodstream. Okay? And the reason why maintaining a very basic minimal level of glucose in your bloodstream is important is because your brain can only use glucose for energy. Okay? It can't access fatty acids and use it for energy. It really needs glucose. So when plasma glucose levels start to decline a bit from that level just after eating, when it starts to get into fasting levels, your insulin levels drop, okay, because you no longer want your fat, muscle, and liver to take up glucose. You want them to spare glucose, keep it in the bloodstream. Okay, so insulin drops. And the pancreas releases glucagon. And glucagon, so if we didn't have glucagon, if we just dropped insulin, okay, certainly the glucose would stay in the bloodstream. It wouldn't get taken up by the liver. It wouldn't get taken up by muscle or fat. But what would slowly happen to glucose after a while? It would start to go down because the brain is taking it up, right? So in order to maintain glucose, we release glucagon. And glucagon acts on the liver very similarly to cortisol. Glucagon acts on the liver to stimulate the breakdown of stored glucose and the gluconeogenesis, the production of new glucose. Okay? Glucagon acts on the muscle cells to promote the release of amino acids that are going to drive gluconeogenesis. And glucagon also acts on fat to release stored fat to be used as an energy source.
Just repeat that last bit.
You bet. So glucagon. Glucagon has actions on the liver, breakdown of stored glucose, and causes the liver to make new glucose. Acts on skeletal muscle to release amino acids that the liver is going to use to make new glucose. It's going to act on fat to release fat, stored fat. Okay? So that the tissue that can use fat as energy can use it instead of glucose. Yes, ma'am?
Do all three act simultaneously as glucagon affect skeletal fat and liver simultaneously?
Yeah, yeah. Yes, ma'am?
Can you repeat the 3 ways that glucose is stored in the skeletal muscle, fat, and liver?
Yes, so glucose is stored skeletal muscle and liver as glycogen, right? And then the fat cells as fat. So it enters the fat and it's converted into, it enters as glucose and it's converted into fat. Yes, sir?
So then, glucagon doesn't release like
glucose from the muscle cells or whatever it's called, like it releases all these amino acids?
So the glucagon does not cause the skeletal muscle to release glycogen, no. The glycogen is specifically for the muscle to use. Yeah, yeah, exactly. Other questions? Yes, ma'am.
So there are, I guess, 3 hormones that we've learned about so far that affect the glucose amino acids, but they all sort of work in different, like I guess growth hormone is more diurnal pattern, and then this is when you eat, and then cortisol is when you're stressed. So how does the body keep those 3 different like hormones from counteracting each other or having to withdraw?
That's a really good question, and every diabetes researcher would like to know the answer. Seriously, right? So the body just does it. The body just manages. So there are, and that's only what I've told you, right? So there are lots of other hormones that affect blood glucose, right? Epinephrine affects blood glucose, right? Norepinephrine released from as a neurotransmitter affects blood glucose. So there are many, many hormones and other chemical mediators like neurotransmitters that affect blood glucose. But the body manages to, it's incredibly sensitive to changes in blood glucose and can correct itself. And usually, without getting too in-depth about it, this is what makes physiology so confusing and seemingly contradictory, because oftentimes when the body does one thing, it also releases something that does the opposite, and it's meant to sort of create a balanced net effect. You know what I mean? So, but this is what makes managing diabetes so complicated, right? Because you have a really really good insulin dosage for your diabetes that works for you, and then you get sick, right? And your cortisol level goes up, and all of a sudden, you're not controlled anymore. Or you go through a growth spurt. You hit puberty, you go through a growth spurt, and all of a sudden, it doesn't work for you anymore. So that's the $1 million question. Yeah. Okay. So, like I said, we'll talk more about the endocrine pancreas in patho when we talk about diabetes. But the most important thing to take away is this: the 2 cells, alpha, beta, the 2 hormones. They're antagonistic. So that means that the stimulus for release is opposite, right? A rise in glucose triggers insulin release. A drop in glucose causes glucagon release. And they have opposite effects on the same tissue type, and that the presence of one suppresses the other, and the absence of one stimulates the other. Okay? Okay, so our last topic for tonight is the control of calcium. And probably more than any other topic, the way I'm going to describe the control of potassium is somewhat of a brainwashing experiment, okay? Because the system for controlling calcium is incredibly complicated, okay? And it's one of these systems that has, that basically nearly everything I'm about to talk about has opposing effects, okay? Where one thing will elevate calcium, the other one will decrease calcium, but the idea is that you get a balancing out, okay? But I'm going to kind of simplify things to talk about the predominant effect of these different hormones, and just to create sort of a better story, okay? So this is story time. Okay. So controlling plasma calcium is incredibly important, right? If calcium levels are too low, the muscle tissue and cellular tissue is, especially muscle tissue, the excitability is very high, and you can end up with tetanus of the muscle and, inappropriate contraction. If calcium is too high, you get the opposite, right? You get muscle weakness and dysfunctional muscle. Calcium is extremely important intracellularly. It stimulates a variety of reactions inside of the cell. It's a second messenger, right? So the way that we control calcium, there's sort of two ideas behind calcium control. There's the control of sort of moment-to-moment calcium levels in the blood. Okay. So we kind of control calcium in a short-term way so that we have a more stable calcium level. And then one step back, we also control basically our total body calcium. Okay. We control basically how much calcium it inhabits our body at any given time, because we want to maintain sort of a constant pool of calcium in which to draw from whenever we need it. Okay. Yes, sir?
Earlier you mentioned too low and too high. Is that blood calcium or intracellular?
So whenever you talk about too high, too low, it's always extracellular. Yeah, and so that's just something to remember, is whenever we talk about hyper anything, hypo anything, it's always the blood. It's always extracellular. Okay. Okay. So we have a certain concentration of calcium in our bloodstream, right, in extracellular fluid, and a normal range is about 8.8 to 10.6 milligrams per deciliter. That's the normal concentration. Okay? Now, the way we maintain that normal range is by controlling all of the sources of input of calcium into the blood and controlling all the sources of output. Okay? So the sources of input, so these arrows that are pointing towards ECF, include, one of the most important ones is our huge reservoir of calcium in our body, which is our skeletal system. Okay? So our bones are composed of a tiny bit of actual cells that are suspended in a matrix of calcium apatate, okay, which is a mineral. It contains a lot of calcium, a lot of phosphate. Okay. So bone is this like huge reservoir of calcium for our body that we can always, it's like our calcium bank, right? We can always make a withdrawal and we can always make a deposit. So one input is breaking down a little bit of bone to release calcium, and then similarly one output is to build a little bone in order to take it out of the bloodstream. The other source of input is our diet, right, and absorption through the GI tract. So when we consume foods that have calcium, your body can't actually synthesize calcium. Okay? Your body can't synthesize calcium. It's got to get it from your diet. So you consume food with calcium, but that calcium in the food that you eat, not all of it is going to be absorbed. There is a control over the extent to which you're going to absorb that calcium. Okay? And there's a couple of requirements to be able to adequately absorb calcium. Does anybody think about one of them? Vitamin D, right? In order to adequately absorb calcium, you have to have vitamin D. Okay? And vitamin D comes from two possible places. The places God intended, right, which is the sun. Okay? You literally can synthesize vitamin D. It's the sunlight hits your skin and magic happens, and you synthesize vitamin D, right? And then the other way is to ingest it. Okay? And since we've put a hole in the ozone layer and cause the sun to not necessarily be our friend, people avoid sunlight, right? They wear a lot of sunscreen. They don't necessarily get enough sun exposure. So oftentimes we have to take in vitamin D dietarily. So there is a control over the degree of calcium absorption, and so calcium absorption can either be enhanced or stunted. Okay? So vitamin D is one requirement, but there's a hormone that can also control, besides vitamin D, it can also control the absorption of calcium. Okay? And then, so there's that gut absorption, bless you, and then there's basically how calcium is handled by the kidneys. So calcium can either be retained by the kidneys if you need it, or excreted. Okay. So the kidneys can adjust the degree of retention, which is another term for that is reabsorption of calcium. Okay. So it can enhance its reabsorption of calcium, or it can reduce its reabsorption and cause you to excrete it. Okay. So those are the main inputs and outputs. The taking it in and out of bone, enhancing or blunting absorption by the gut, or enhancing reabsorption or reducing reabsorption, okay, by the kidneys. So there are two hormones involved in calcium control. They are antagonistic hormones. One of these hormones acts in a very specific, there's really one way to influence calcium, and that's mainly through interactions with bone. Okay? And then the other hormone acts on everything. So the hormone that acts on everything is parathyroid hormone, PTH for short. And the hormone that tends to act simply by interacting with bone is calcitonin. So parathyroid hormone is produced and released by the parathyroid glands. And as you'll see in a moment, the parathyroid glands they're called parathyroid around the thyroid because they're located behind the thyroid gland. Okay? And then calcitonin is produced by those parafollicular cells, or those C cells, that were inside of the thyroid gland. Okay? I sort of mentioned them, but I didn't focus on them. So parathyroid hormone, when it's released, it tends to bring about an elevation of plasma calcium. Okay? So parathyroid hormone, when it's released, it brings about an elevation of plasma calcium. And it does that in a variety of ways. Calcitonin, when it's released, tends to bring about a decline in plasma calcium. Okay? And since I told you it primarily works by interacting with the bone, what does it tend to do then? Does it tend to build bone or break down bone? Build, right? So calcitonin, and that the two terms for bone breakdown or building up of bone is deposition, is building it up, and resorption means breaking it down. Okay? So deposition, deposit, right? Bone deposition is taking up of calcium, building bone. And resorption is the breaking down of bone to liberate calcium. So they're antagonistic hormones. So that means that their stimulus for release is opposite. So a drop in plasma calcium stimulates the release of parathyroid hormone and inhibits calcitonin, while a rise in calcium stimulates calcitonin and inhibits parathyroid hormone. Okay? Antagonistic hormones. So In this slide, we're looking at the back of the thyroid gland. We've done a cross-section of the pharynx and, the larynx and the trachea. And you see these little 4 blobs behind the thyroid gland are the upper and lower parathyroids, okay, that produce parathyroid hormone. And then those parafollicular cells, or C cells, that produce calcitonin are the other cell type in the thyroid gland. Right? Okay, so calcium inputs, just to review, calcium inputs, meaning calcium into the plasma. Bone resorption, breaking down bone, liberating calcium. Renal reabsorption. Reabsorption equals retention. Right? Reabsorption equals retention. And intestinal absorption, which is enhanced by vitamin D. Okay? Those are all ways to increase plasma calcium. Ways to decrease plasma calcium: bone deposition, right? Building new bone. Decreased reabsorption by the kidneys. Okay, so basically not retaining it, excreting it, and decreased intestinal absorption. Okay. So in this slide here, I'm describing plasma calcium levels as being the primary thing that's going to stimulate this system, right? But there is an important relationship to understand between calcium and phosphate in the bloodstream. Okay? Calcium and phosphate, and we're talking about calcium that's dissolved in plasma, phosphate that's dissolved in plasma. Calcium and phosphate, when they are present together in the bloodstream, they tend to attach to each other. They really like each other. Okay, they're really good friends. But when they are attached, basically, if you are measuring the amount of free calcium, if calcium is attached to phosphate, it's low. So that means that a rise in phosphate in the blood will tend to cause a decline in calcium. Okay? So if plasma levels of phosphate rise, that's going to be equivalent to and cause a drop in calcium. Okay? And phosphate, there's a lot of phosphate in everything that we consume, especially processed foods. There's like a lot of phosphate in processed foods. Okay? And thankfully, our kidneys are really pretty good at eliminating excess phosphate. But there could be situations where phosphate levels transiently increase. Okay? And a rise in phosphate is going to, in terms of this system, a rise in phosphate is going to be interpreted exactly like a drop in calcium. Okay? Okay. So, this is a cross-section of a type of bone that we call compact bone. Okay? There's 2 types of bone in our body. There's compact bone and what we call trabecular bone, which is looks very different than this. Trabecular bone is the bone that's in structures like the hip bone, and it looks kind of like this spongy, loose bone tissue. And compact bone is, so the ends of bone also have trabecular bone. You can see that kind of sponginess. But the cross-section of the middle part of this long bone is, it looks like this, it's compact bone. So if we look over here at this part of the slide, what we notice is that with compact bone, we have cells, osteocytes, that are suspended in that matrix, right, that calcium appetite matrix. Now, these osteocytes, there are two very specific varieties of osteocytes. There's something called an osteoblast and osteoblasts. And the word blast tends to mean a cell that produces something, right? So an osteoblast is a bone cell that tends to produce more bone matrix. Okay? So osteoblasts tend to enhance bone deposition. They cause bone deposition. And then osteoclasts, anything with the word clast, tends to mean you're breaking down something. So osteoclasts stimulate bone resorption. Okay? The only reason I'm showing this, the only reason I'm mentioning this, is because when we talk about something enhancing bone deposition or enhancing bone resorption, they're going to be stimulating these two cells to do it. Right? It's just the mechanism. And then good old vitamin D. Okay, so we know we need to have adequate levels of vitamin D in order to absorb calcium in the intestines. Okay? Now, vitamin D is, like I said, either synthesized through light exposure, or you consume it. But the form that it takes, whether it's the initial synthesis or the consumed version, is vitamin D3, which is an inactive form of vitamin D. So when we talk about you have to have adequate levels of vitamin D, you have to have adequate levels of that inactive form so that your body can then control the activation of it. Okay? So vitamin D, the activation of vitamin D, there's two steps. The first step happens automatically. Okay? The first step is the processing of vitamin D by the liver. Right? It just adds a hydroxyl group to the structure. And then the second step is the addition of another hydroxyl group that is under hormonal control. So the last activation step for vitamin D is controlled by parathyroid hormone. Okay. So I told you parathyroid hormone increases plasma calcium. So what do you think parathyroid hormone is going to do to vitamin D? Is it going to inactivate it or activate it? Activate it, right? So parathyroid hormone is important for the activation of the final activation of vitamin D. Okay. And as you can see, okay. So this purple box right here, that arrow should be pointing up. Okay? So that purple box, that arrow should be pointing up. Okay? Because what stimulates parathyroid hormone to activate vitamin D is going to be either a drop in plasma calcium or an increase in phosphate, because those two are equivalent. Does that make sense? So what's going to stimulate parathyroid hormone to trigger vitamin D activation is either a drop in calcium or a rise in phosphate that's going to bring about a drop in calcium. You bet. what's going to cause parathyroid hormone to activate vitamin D is either a drop in calcium or a rise in phosphate, because that's going to cause a drop in calcium. Okay? All right. Last slide. Woohoo! All right. So I'm going to tell you, this slide, it makes sense to me. All right? Because I created it. And it was an attempt by me to try to summarize all of these components. Now, it may not be all that meaningful to you, so I suggest, if it isn't, for you to create one, okay, to summarize all of these things. So let me walk you through this one, and then that might stimulate, and I actually recommend, whether this one makes sense to you or not, make one for yourself, okay? Because the person that benefited the most from this slide is me, right? Really, because anytime you have to synthesize and summarize something in like either a diagram or whatever, that actually is what learning is, okay? So I recommend that you, because there's a lot of moving parts to the system, I recommend that you put it together on your own, right? So first of all, we've got plasma and extracellular calcium. And plasma is extracellular fluid, right? So I'm just being thorough. So we've got calcium in the extracellular fluid, and then we've got all the inputs and outputs, right? So input through breaking down bone resorption, or the output by depositing bone. And then we got the kidneys, right? Enhanced reabsorption causes more calcium to go in the plasma, or blunted reabsorption causes it to be excreted. Okay? And then we've got intestinal absorption, enhances plasma calcium, and the activation of vitamin D is going to be essential for that GI absorption. Everybody good with that? Those components? Questions? No, it's okay. Go ahead. Why is? Okay. Awesome. Yes? Yeah.
So why are the kidneys connected to the intestine there?
Because, that's a good question, because the final activation step is actually done by kidney enzymes. That's something I didn't mention. Okay? So PTH stimulates kidney enzymes to actually activate vitamin D in the final step. Okay? All right. It's almost there. We're almost there. So, okay, so now we have all of the appropriate arrows going in the appropriate directions. Now, up here in this box, whenever PTH is elevated, whenever PTH is released, it enhances all of these plus signs. Okay? So when PTH goes up, we have more bone resorption, we have more renal reabsorption, we have more vitamin D activation, and gut absorption. And it causes plasma calcium to rise. Okay? And whenever PTH goes down, all the negative signs are enhanced. Okay? So we have more bone deposition, we have less reabsorption by the kidneys. Okay? And then calcitonin enhances bone deposition. Okay? And then up here, what determines what direction PTH and calcitonin are going, right? Whether they're released or not released. A rise in calcium suppresses PTH, stimulates calcitonin. A decrease in calcium or a rise in phosphate is going to increase PTH and decrease calcitonin. Okay? Yes, sir. Questions?
Always working,
Say that again?
one always working, PTH, calcitonin. Is that one, are they antagonistic like this?
Yeah, so they're antagonistic, which means that they are not released at the same time by and large. What was the first part of your question?
Yeah.
Yeah, so they're classic antagonistic hormone. Yes, ma'am. Do they go and live in the bone? It's bound together, going around in extracellular fluid, and it's going to get excreted that way. Yeah. I don't think so. I don't think that calcium bound to phosphate can manage to get into the bone. I'm not that's a good question. I'm not sure about that. I don't believe so. Okay. So